So, welcome to Calculus. I am Mr. Patillo and I will be explaining to you these concepts. So, I want to begin Calculus with Chapter 2 in this book because Chapter 1 is basically remedial material, and at this point you guys should know it. So, we'll start in Chapter 2.1. And if you need a review how to do it, you can look in Chapter 1 in the book for your help for that. So we'll start off with limits right away. And so, section 2.1 is limit of a function. We have four major goals in this section. We have informal computation of limits, secondly, we have one-sided limits, thirdly, we have limits that do not exist, and that D and E means do not exist, by the way. And lastly, four, we have the formal definition of a limit. And because I don't want to yap for 2 hours, formal definition of limit, and more than likely, limits that don't exist will be covered in the next video, and not this first one right away. So, first of all, we want to get an idea of what in the world a limit is. So, we're familiar with this wonderful sign that you can see. And now you're about to see the greatest piece of artwork since Van Gogh. The speed limit sign, which, as you know, in California is a suggestion. So it's better known as the speed suggestion sign, because if you drive the speed limit, you'll get ran over. So the idea of a limit is something I can go past or something I can be less than. So, right, the speed limit is of course the legal way you're supposed to go. But nobody really follows it, as we all know from our own driving experiences. So the idea is I can be more than this limit or less than the limit itself. So I can either be more, less, or directly at 55. And in light of this is kind of how I want to approach limits. So from more or less point of view. Okay. So on your speedometer, which looks something like this, here is 55 miles an hour. Right? You'll have to deal with my horrible drawing. You can either approach 55 miles an hour. Here's 0 down here. You can either approach it, so this is actually coming from the left side. So when I approach it, getting larger and larger, I'm going from the left side, or I can slow down to get to this limit. Right? the idea that the limit is the thing that's stopping us, I can also slow down. Okay, and that's going to be coming from the right side to reach the limit. I don't have to. Right? The idea is we're trying to stay at this limit, even though you can go past it or above it. The idea is to stay at it. You can either get to the limit by coming from the left side, or slow down to it by coming from the right side. And as you know, when you see the red, whites, and blue flashing lights behind you, you know to slow down to get to this limit. Similarly, we talk about the mathematics in this way as well. So let's draw a picture of a function and let's talk about it. Okay? Oops. Let's erase that. So here's our function. So here's the graph of f of x. It looks something like that. Okay. Okay. Let's say I'm trying to find out a number exactly at this point right here in this function. It doesn't have to be there, I could have been anywhere. Okay. So this is the point that I want. I can do one of two things. Oops. I can either come from the right side, make it smaller to get this point, or I can come from the left side to get larger, increasing to get to this point. Now, why is it right and left side? Right? Because, of course, as you know, this is coming from the left because of your axis of rotation. So, thusly, as such, this number that I'm approaching is defined to be the limit. And this number that would be here would be called C, or the number that we're basically trying to figure out what it is. Okay, this is C, as your book defines it. Now, you need a big, fancy, formal definition, because what's life without a formal definition to work with? So, let's give you the informal definition of a limit. Write this down. So it says that f of x can be made arbitrarily close to a unique number L by choosing x sufficiently close but not equal to c. So that sounds like a mouthful, and if it sounds like a mouthful, it is a mouthful. Let's translate that into proper English, shall we? So, to better explain what this means, what it's saying is I can approach it. What this says is I can approach from the right and from the left, but not the exactly same. But not C. And it's very important to try to see. And we have what we call limit notation. So this is the limit as x approaches C. And this is red. The limit of f of x as x approaches C is L. So that's how you read this notation that you'll see. The limit of f of x as x approaches C is L. Okay. Now, back to what I'm saying here. Back to this point. When I'm saying that I can approach from the right side or from the left side, coincidentally, these things have to be exactly the same. In order to have a limit, the number I approach from the right and from the left have to be the same. So in order to have a limit, the number I approach from the right and the number I approach from the left must be the same. This is the concept of one side. This is the concept of one-sided limits. Okay. The concept of one-sided limits is right hand and left hand side. So I'm going to write a very important theorem right here. I'm not exactly going in the order of the textbook, but that's okay. So a right-handed limit, please write it down. Says the following. We write the limit is x approach. The limit of x of f of x as x approaches C from the right, just with the positive sign. Equal to L if we can directly to the right of C. Okay. On the interval C to B. And then left-handed limit we write the limit of f of x as x approaches C from the left is L. If we choose x immediately to the left, of C on the interval A to C. Okay. Going back again to my picture, not this one, back one further. Going back to this picture right here, what does this mean in this context of this picture? What I'm saying here, if this is L, on this side I have the limit x approaches C from the left of f of x, and on this side I have the limit as x approaches C from the right of f of x. Okay. In this situation, C is the smaller number. In a situation, in the left-hand situation, C is the larger number. So in my interval here, this is going to be, I can write an A here. I can put a B there. Okay. With it. So everybody follow what's going on, the idea of right-hand, left-hand limits. So that I'm approaching something from the right, I'm following this path to get to this point. I'm following the path from the other side to get to the point. So that's the idea behind right-hand, left-hand limits. And there's, of course, the theorem, which you're going to need to memorize, but we'll get to that. So now that we have an idea behind what's going on, let's do an example of what the heck this is. Continue. So here is example 1. We're going to guess the limit. That's the limit of f of x equals x squared minus 2x minus 3 over x minus 3 at x equals 3. Okay. Now, recall from algebra, of course, from algebra, because 3 is in the denominator, 3 is excluded from the domain of the function. Now, as you can see, this is a factorable equation, and you can factor this to show what happens in this situation. You learn that later. Baby steps. So I do not define it like that. So in our situation, x equals 3 is excluded, right? Not in domain of f. And as you'll So the idea here is to create a table of values so that this occurs. So now, we create our table of values by doing this. You guys know how to draw a table. This is x, this is f of x, and we're choosing it at x equals 3. Now at 3, I happen to know that this is undefined. So now I need numbers that are close to 3, but not at 3 itself. So let's try 2.997 and 3.001, like that. And say 2.9 and 3.1 for completion purposes. Okay. Now we plug in numbers into this function, and you guys are algebraic geniuses, so I don't need to tell you how to do this. So when you do this, so we go 4.001. Will of course be 4.1, and then 2.997, so it'll be 3.997, this will be near 3.9. Now, as I can tell here, as I can see, the number is approaching 4, because it gets really, really close to 4 here, and it's just slightly above it there. As such, we can kind of guess the fact that it happens to be 4. Okay. So to guess at it, we can guess by our deductive reasoning. By our deductive reasoning here, we can see that it's getting very close to 4. So we can say the limit as x approaches 3 of this huge ugly function over x minus 3 happens to be 4. Now, coincidentally, looking at this, if I graph this function, it's of course a linear function. It happens to be a linear function. Can't really draw, but it'll do. I apologize for this horrible picture, but it'll do. There's a hole at that graph. There's a hole at that particular point. Why? Because the denominator cannot be 0. So it is very important for you to see that in the situation, a limit does not have to be part of a function at all. But the idea is that it's approaching a particular number. The idea that it's approaching a particular number from either side. So everybody understand that the concept of the idea here. Now, since that was a fun example, let's do one that's a little bit more difficult. Yes, the limit as x approaches 0 2 square root plus 1 minus x minus 2 over x squared. And so this is the example that's in your textbook, so you don't really have to copy it per se, but I want to point out something very important in this problem. It looks algebraically like this is an impossible problem, because 0 is of course not in the domain of function, but it's perfectly plausible to do. And this is a situation that can happen from time to time, because your calculators are not all that intelligent. So if you try to be too accurate with the situation, the calculator will give you false positive or false situation, false answer. So I'm not going to sit and copy the problem that's in the book. It's already in the book for you. So, but I'm just pointing this out in the sense that your calculator is not a guarantee for doing limits by this approach. So it's very situation that you need to be aware of. So when you're choosing numbers, try, as a general rule, go to thousandth place. When you're choosing your numbers. As you see here, they show you what happens when you do that. So it's very, 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 very important. Right, and of course you can see the answer is a 1/4 from the book, but the book has the work for you, so I'm not going to copy it for you. It's an embarrassment, so I don't want you to copy this problem. I just wanted to point that out, that your calculator can make mistakes. So, therefore, let's get into your first theorem of calculus. Okay. So theorem 2.1 is going to be the one-sided limit theorem. I'm going to talk about that in a second. The two-sided limit as x approaches c of f of x exists if and only if and in future notation I will just write this as IFF, if and only if. So if and only if the two one-sided limits one-sided limits, meaning the right-hand side and the left-hand side, exist and are equal. Furthermore, if limit x approaches c of f of x equals L, then limit as x approaches c to on the left is equal to L, and the limit as x approaches c from the right of f of x is equal to L. So this is your big giant theorem, your first theorem in calculus. Now, I stated this earlier, which basically says that I stated this earlier in this presentation, earlier in this lecture, not here, not there, right here. The number, what I stated here, the number I approach from the right and from the left must be the same to have a limit, which is effectively what I just told you just now. So I'm going to put that again, I'm going to put that note again. Number approach must be the same from the right and the left in order to have a limit. Otherwise, it does not exist. Otherwise, oh dear. Okay. The limit does not exist. Okay? So that's actually touching upon objectives 2 and objective 3. So when we talk about one-sided limits, I mean limits from the right and a limit from the left. When I speak of limits that do not exist, I speak of a situation where the right-hand limit and left-hand limit are different. The book uses the term one-sided limit, but I use right-hand and left-hand side because it's what I'm more comfortable with. Okay. So everybody follow that. Okay. So to visualize this theorem, so I'm going to write, this is kind of a visual of the theorem 2.1. Here's my half. This is my number from the right. Here is my C. Okay. This is the limit. Let's not do that. Wrong color. This is the limit coming from the right. So this is the limit as x approaches c from the right of f of x. Excuse me. Okay. And this is the same limit. Just pretend it's the same number. Okay, this is the same limit coming from the left side. From the right side. Oops, sorry. This is coming from the right side here. I mislabeled it. Okay, this is from the right. This is from the left, actually. Mislabeled it there. So that's coming from the left, that's coming from the right. So let's put it correct. Alright, and so this is the left limit, this is the right's limit, and then together, combining them, they form one proper limit. C. Can't really draw, but it's supposed to be the two different functions together. Okay? And so this is showing you that when they're the same number, it doesn't, it will have a limit. Okay? That's limit x over to c f of x, like that. So it's a visual to help you see that. Now, a term you'll hear later in calculus is two terms called convergence and divergence. And you'll talk about it when you get to series. And we can apply these terms to limits as well. So, I'll define these for you real quickly, and then we'll conclude lecture. So, to define convergence, is when a function approaches a number. So that's definition of convergence. So whenever function approaches a number. So all the limits that we have talked about to this point are what we call converging. It converges. It approaches something. It's coming towards something. I don't necessarily know what that is, but it's coming towards a number which can be found mathematically. That's convergence. So in example 1, you can be said to converge to 4. It could be said that f converges to 4. In example 2, you could say that f converges to a quarter. Okay. So it works like that. So convergence is when you approach a number. It's very, very, very important. Okay. And when we talk about divergence or divergence, not to be confused with the movie that just recently came out. We talk about divergence is when a function is unbounded or oscillates. Okay? So to visualize this concept, what do I mean when I say convergence? Okay, convergence is when I can find what that number is. So for example, it's going towards like this, and there's your limit, there's your C. This is converging. It converges because it's approaching this number, this limit here. So this is convergence. It's divergent or divergent when either of these situations happen. It's divergent when something is unbounded, like this one. You see how it rises and goes all the way up without ending. Okay, so divergence is when it's unbounded. Okay, And I'll explain more in detail in the next lecture what I mean by these terms. Yeah, but I want to give you an idea of what these terms are before you went into detail of, or when it oscillates. So its oscillation is something like this, like sine function. Okay. An oscillation, something like that. And I'll explain more in detail what we mean by that later. Okay. Now, that should conclude today's lecture. How am I doing on time? I'm yapping my mouth too much. 46 minutes. Okay, yeah, we need to stop. Oh yeah, we need to stop talking. So, go back to here, my full screen. So I've yapped a lot. And therefore, today's lecture, therefore, your homework for today, or what you should be able to understand after listening to me yap, pages 53, 55. Okay, we'll talk more in detail about it later. And I'm going to continue with the concepts of limits that do not exist, convergence and divergence in the next lecture. And on 2, I want you to do page 59. Numbers 1 through numbers 1 through 9 should cover you. And if you have questions, you can ask them, but for now, that will be good. And we'll cover, even though I won't do homework problems for you in class, we'll cover the points of convergence, divergence. We'll cover all of this in next lecture point. So, there we go. Have a good day.